between like a conductor and an insulator. They have high mobility and they conduct electricity really well. And that's why we are making device out of it using column 3, aluminum, gallium, and indium, and we are all combining with nitrogen to make indium nitride. So semiconductors, we make device out of it. So this right here is the blue light. Sometimes you can see it in cars. They are mostly made from gallium nitride and low composition of indium. But if you want to make something like this, you need high composition of indium. That is what we're trying to perfect right now, is making colors besides blue, like red or yellow or green or something like that. So the main problem with growing indium nitride is that they have high decomposition. So here, before they decompose at like 400 degrees, and then here with the hydrogen. So in order to fix that problem, we will add nitrogen plasma, and that will shift up to 600 and sometimes even 800. So yeah. And this part right here is basically, this is a calibration. Most of the times the temperature in the lab is always broken, the thermometer is always broken. So this is here to verify the temperature. As you can see, if you increase the power, then the temperature will rise. This is a band gap. So basically, gallium nitride is right here, which we already did. Before I came. Now we're doing indium nitride, which is all the way down to infrared. If you add gallium nitride and indium nitride together, you get this little rainbow right here. This is what we want to see. The blue light is right here. But if you add more indium right here, you can see all these red and orange colors. And that is what we're trying to find right now. Usually silicons are usually related to semiconductors, but because silicon has a lattice constant over 3.7, which is really bad, so we don't use it. So how we grow the semiconductors, the indium nitride right now. So basically you have this sapphire wafer, and that is Al2O3. We're trying to get rid of the oxygen, so in order to get rid of it, we have to add hydrogen to it. And at the same time, we have to keep pumping the nitrogen plasma, and that's going to be a really big part because it's going to keep running. And while that, we're going to add the TMI, which is the trimethylanium, and that has indium in there and some hydrogen and carbon in there. At the same time, we're going to keep adding nitrogen. And the plasma is coming from the radio frequency halocathode, which is like right above this plasma method. I don't have a picture of it. And after that, you have this buffer layer of indium nitride. And in order to get rid of TMI is C3H9. You want to get rid of the CH3. So in order to get rid of it, you have to add you have to increase the temperature, sometimes to 800 degrees to decompose it. At the same time, you're going to keep adding nitrogen. You're going to flow in there, and this is what you're going to get out of after growing it for maybe 2 hours or something, or over that. I actually have a sample right here. This is what it looks like. It looks kind of like a mirror. This is indium nitride, so you can pass it on. Just don't open it. You can pass it out. Just don't open it.
So how do you open it?
Don't open it. Yeah, don't open it. You can pass it around. Yeah. So this is just a drawing of it. So this part right here, which is not in the picture, that is where the plasma nitrogen plasma is coming in. And that's the plasma fed, and it's going to go all the way down here. This is the hydrolyzed. We don't use it now because we don't need to add hydrogen anymore. The spectrometer right here, which is this blue line that measures the spectrum. And there is the reaction chamber, and these are all the colors of the gas. They're all different colors for a different gas. This is on a molecular level. So that is where the nitrogen plasma is coming in. So we know that growing the indium is really hard because of the higher decomposition and the higher nitrogen equilibrium pressure. So we're going to add more energy to stabilize the indium nitride. And we use this halocathode to add the plasma instead of ammonia, because ammonia has hydrogen in there, and we don't want the hydrogen, because that will increase even more the decomposition rate. Yeah. And let's see. So after growing it, we have to put it in the FTIR, which is the Fourier transform infrared, and that is just a technique to like identify all the organic and inorganic materials, but we already know what material it is, so we only use it to find the thickness of the film. We also use it, UV spectroscopy. It is also, they are the same characteristic, but they are on different they just measure the different wavelengths. So here is the FDIR, and this is the UV. They measure the same thing. And what they measure is the thickness. They also give you the dielectric, and they also give you carrier concentration, and all these processes, the elastic scattering, which means the kinetic energy is like conserved and stuff. And after the FTIR, we are using Raman, which is this is like, oh my God. It's a technique to measure the inelastic scattering of the light, and it would determine the vibrational modes of the molecules. That's how you get the Raman. And here it would start from, well, the laser. It would start here, and it would start laser to the sample, and then there's like a giant machine back there, and then it would bounce off basically a couple of times, and it keep bouncing off until it reach to the detector, and you can extract the crystalline carrier concentration and the defects from it. And this is the experimental results. So this is what you get out of. And if you put it under a microscope, if you magnetize like 20 times, you'll get a picture like this. And this is a dot. This is the defects. We don't want to see that, basically. This is from the FTIR. If there are more fringes, these are the waves, then that means there's more thickness to it. As you can see, if it's gallium nitride, there's more thickness from gallium nitride. But this indium nitride here, it looks like a straight line, but it's not a straight line. If you actually program it, it will look something like this. This is the experimental data from here, from this part right here. And this is the graph you get. And you have to fit it in order to find the thickness and the roughness of the film. Raman. So basically, where you get these peaks right here is from the vibrational nodes of the molecule. So if these like these atoms, when they vibrate, this is where you get the peaks. Yeah. Oh yeah, this part right here is the crystalline, this part here is the carrier concentration, and this is where the sapphire is. This is data. I spent 2 months working on this math right here. This is the only math I learned in 2 months. How do you grow? It's finding the thickness of it. How do you find the thickness? Is you multiply the growth rate by the hour run. So this is run for 1 hour, and the growth rate is right here. So if you want to find the thickness, you can multiply 42 times 1, and you get 42 nanometers. Yeah, and here's another one. This one is on 2-hour run, but this is on a 3.8 pressure. Oh, this is a 2.2 pressure tour. And this pressure is 4.2, and this is a 4-hour run. As you can see, when you increase the pressure, you have to, every time you increase the run, you have to increase the pressure in order to ignite the nitrogen plasma there. If you increase the power with the pressure, this pressure is increasing with the increase of pressure in order to, yeah. And this is the plot that you plot out. And this, the atomic ions and the growth rate, they look the same. And that means it will contribute. So that means atomic ions contribute to the growth rate. These bottom here, the molecular species and the atomic neutrals, I don't know why it's there, but I'm putting it there to show there is no correlation in the growth rate of growing the indium nitride. These are from my mentors. I didn't make any of this, by the way. Yeah, I forgot what else is there. And this is also the same plot. The only difference we change is the pressure and the power. As you can see, it gets better. These peaks are getting better and better, which is good. We want a better peak. If it's a sharper peak, it means that this crystal line is really good. If it's broader, if it's more wider, that means there is defects in there. If this part of the graph is shifting, that means it's like have some stress and strain on the film. This part right here is the carrier concentration. If it's more broader, then that means there's more carriers in there. Yeah. So that's my conclusion, what I found. And for sure, we're gonna, well, I don't think I will, but I don't think I ever will. It's checking the surface of it, which is on a micro, really micro scale, using the atomic force microscope. There's like finding the, what's it called, the tips of it or something. And then we also going to investigate the transport properties, and we also investigate the alloying of gallium and indium nitride. And I don't know why there's no page left. There's some, well, there's something I want to thank people there, which is my professor, or it's just my, why is it not on there? Oh, there it is. Never mind, sorry. Oh wait, never mind. So these are I want to thank. They changed my life forever, really. I just realized I hate physics from now, so these are the people I really want to thank now. And yeah, the end. Any questions? Oh my God.
Hi, do you have any questions for Lisa?
What's the reason for using sapphire as a substrate? Can you use other crystals, or why is this one the best?
Because when you decompose the aluminum, but then if aluminum doesn't really affect anything, it stays there. So then I mean, I guess you can use other ones, but I don't know.
If you want an answer, I can give you an answer.
Oh yeah.
It's close in lattice constant. So you saw the lattice constants that were listed at the beginning there. Basically, sapphire, the way that's cut right now, is pretty stable, and then it has a lattice constant that's closer than that. Most of the nitrides, so that we can work with it using a buffer layer to be a bit of a transition. Then we can grow off of that, and it's cheap.
Oh, it's sapphire?
Relatively speaking.
I'm guessing it's because the sapphire is not mined sapphire, right? It's growth.
It's grown sapphire, yeah, it's synthetic.
All right, let's thank Lisa. And we will now go from small back to very big, and welcome up Garrett.
I noticed that.
Yeah. You guys did service by not having you be able to actually practice using other.
Yeah. I'll use it sparingly. Okay. Well, good afternoon, everyone. Thank you all for coming and not running out during the break. That was nice of you. My name is Garrett Polak. I am under the advisement of Dr. Michael Crenshaw here. And my topic for the summer was gas kinematics and ionization mechanisms in galaxies. And that's bringing up some questions. First off, what is a Seyfert galaxy, and am I pronouncing that correctly? I'll answer this one. A Seyfert galaxy composes about 1% of all nearby galaxies. It increases in number as you go farther out to farther redshifts. They are characterized by strong high ionization emission lines. And if you look directly into the center here of this galaxy, and you zoom in, you'll see what's called an AGN, active galactic nuclei, and I think you might recognize this from like 10 minutes ago, but this one's in color, And if you zoomed in all the way to the center of the galaxy, you'll find the supermassive black hole surrounded by an accretion disk, and that is surrounded by a thick molecular torus here. Seyferts are divided into two categories in themselves, Seyfert 1s and Seyfert 2s, because scientists are great at naming things. If you look this way, which is above the plane of the disk, that's a Seyfert 1. You can see inside of the middle to see the broadline regions, which were those thicker molecular lines. And if you have a Seyfert 2, you're looking at the torus, which is obscuring these broad lines. You're only getting this narrow line region here, which is what I was working on. So now that you know my topic, what was I doing this summer? The first objective I had was to analyze and sort all of our data. So our team has collected a bunch of data from all the way back until 2013, way before I was here. And some of it got corrupted, and we weren't sure when or how, but I was going through all of it to see where that corruption happened, where it stopped, so that we could get quality data and see if we had to change anything from the past projects. My second objective was to use the quality data that we got to then gather more information on Seyfert Galaxy Markarian 3, which I'll go over in a little bit. I hate this thing. Part one, the data. Where are we getting this data from? The first thing is the Hubble Space Telescope. On the Space Telescope Imaging Spectrograph, which is on Hubble, it gives us a 0.1 arcsecond slit, which is pretty narrow, but it gives us some pretty good resolution for this. The second one is the Apache Point Observatory's Dual Imaging Spectrograph, which is a larger slit, and here is an example of these. This blue line is the STIS data. These yellow lines are a bunch of different position angles from APO. You can clearly tell the difference between the thickness of the slit. So once we received this data, I went over our what we call standard stars, which is the things that we use to quantify the brightness of these galaxies. And what we have was a bunch of spectral images of these stars. So here's an example of a spectral image for one of these stars, BD33. As you can see, if you go from left to right on this image in the cross dispersion, if you filter this through this slit, it spreads out the light from this star, and you get what looks like this. All across here, there's different wavelengths. And this is a good image. The bad image, I don't know if you can tell, but down here is a bad image. If you go from left to right, it gets a lot skinnier. And there is a little halo over here that was being projected onto this spectral images basically because of condensation. Thank you. Condensation on the lens of this APO observatory, causing some sort of halo effect on the left-hand side of some of these images. And that would definitely spell bad news for the rest of the data that we were using. So I went through and took a cross-section of all these spectral images and developed something that looked like this. So if you just take one x-axis pixel and you spread it out and get a brightness profile for this star, you get what look like these, the good and the bad. If you can see on the bad, you get what look like little wings. We call them wings on this little Batman thing here. And those are bad. We don't want those because they contribute to the overall flux, and it gives you way more flux than you would normally attribute to these stars. So I went through and also got the full width half max for all of these stars, which is the amount of velocity from each. I'll talk about that later. So I went through all these stars for each date and for each star and for each exposure on each date all the way back till 2013, looking at their full width at half max, which, if we go back now, is the thickness of this line as you move across the x-axis. So if you are on the left side, the full width at half max of the corrupted image would be a lot wider than on the right side. And so what I did was go through it and see if that full width at half max changed drastically as you moved across the x-axis on these stars. I also recorded notes to see if there were any of these wings. And after doing that for hundreds of these exposures, we got what was good data and what was bad data. And from there, we were able to narrow down which dates for our Markarian 3 observations were actually decent to use and which ones were bad to use. So here's Markarian 3. This is my second part. This beautiful image right here shows that it is a S0 galaxy, which means there's very little star formation. It's a very old galaxy. It's a Seyfert 2, which from the beginning means that you don't have any broad lines. You just have these narrow line regions. And it is around 55 megaparsecs away, which is, it's not too far, but it is far enough that you don't really see, it doesn't really look like a galaxy. And it is interesting because there's a tidal stream coming from a nearby galaxy, this UGC 3422, which is intersecting this gas from this galaxy, and it's causing this misalignment of the stellar and gas disks, which this gas disk here, does this work? Yeah. This gas disk here is coming in from this other neighboring galaxy, whereas the star disk is like this. So it is very interesting. And that is why it was important to qualify this data, because otherwise we would have no idea what's going on. And if these halo effects were causing the spreading out of this full width at half max, it wouldn't be good. So I went through and quantified the data and took out 2 of these bad position angles from APO. So we did these 5 observations. 3 were good, this 30 degrees, 90 degrees, and 129. And 2 of them were bad, these 60 and 150 position angles. And then with STIS, we only had 1, which was the position angle of 71. And with that, I took all 5 of these position angles, and we ran a 2-component fitting, which was designed by Travis Fisher. And we ran a Gaussian fitting routine for these O3 spectrum. And what this does was attribute 2 different gas components to each of these spectrum lines along this slit, for each pixel along this slit. And what you're basically seeing here is that this gas is divided into 2 components, one moving toward us, one moving away from us, or at least blue shifted and red shifted as compared to the systemic line of the O3 emission. Nice little cartoon here, that's cool. And what we did with this, along each point of the slit for every position angle, 30, 60, and 30, 90, and 129, as well as the 2 Hubble Space Telescope position angles at 71, we came up with some results in the form of 3 different plots. And by 3 different plots, I mean about 3,000 different plots, which ended up being 3 good plots. The first ones look like this. These are my kinematic plots. The data was sorted by peak flux, meaning that of those 2 components, which ones had the higher flux. As you can see here, this first component was all of the data points that had a higher flux, and a second component was, the ones that had the second highest flux. And with that, the rest of these were plotted for velocity and full width half max. And what we took away from this data was that it's clear to see the presence of AGN outflow. So as compared to the rotation of the galaxy, this AGN outflow is what's causing this bump in full width half max from around -3 to 5 arc seconds, as well as a little bit of a bump in the log flux. And you can see the blue shifted and red shifted components of this rotation. So what that means is that from the left to the right side of this galaxy, you can see that this movement is coming either towards you or away from you. And it's a lot easier to see with my next plot, which look like these, which I thought were very pretty. Here, if you go along this position angle, you can see the red shifting and blue shifting, and that gives you a clear rotation of a clear picture of the rotation of this galaxy, as the blue shifting is coming towards us, the red shifting is going away from us, and this actually corresponds to the major axis of this galaxy, which is perfect because you can see it directly here. And this is for the first component. The second component, as we plotted here, gives you a clear outflow from the AGN, which is completely blue shifted, as all of this outflow from the AGN is coming directly at us. And I thought it looked very nice. And so the third plot that we get is what's called a BPT diagram. It stands for Baldwin, Phillips, and Tellerman. And this uses the emission line ratios determined by all of these other points to give you what's the most likely cause of the ionization of the gases coming from these galaxies. And there's about 9 different ones of these for each position angle. And the blue is the first component, the red is the second component. And depending on where it's plotted on this graph, you can tell where this ionization is coming from, whether it's from the AGN, or whether it's from H2, or whether it's from a weak AGN source, which is called liner. If it was in this H2 region, that would correspond to star formation. And like I said before, there is very little star formation in this galaxy, which is why most of it is located up here by this AGN. And with that, I would like to acknowledge all these people and thank you very much for having me and putting up with me. Is there any questions? Cool. I know. Covered all my bases, I hope.
So I have a question. You want to go back? It's just that you probably said it and I just missed it.
Go.
What's the difference between the left plot and the right plot?
Here?
Yeah.
So I divided it into the two components here, the first and second components. And so the left is the first component, and the second is the second component. So the first, let's see.
Component means what?
So these are two components here, these red and blue Gaussians, which we fit to the data. So it's basically two different gas components going in two different directions. Yeah. So it's all the same cloud of gas, but there's two components of that gas that are behaving differently. And so we chose that there was two because that gave us the best fit, but there could be 3 or 4 different components of this gas moving all together. Yeah, so there was 2 different components, and that gives you these 2 different rotational velocity, just basically velocity graphs. Yeah. Yes?
Why was some of the data bad? Where did the halo come from?
There was condensation on the lens of the APO observatory. Yeah, I narrowed it down to like September of 2017, and so ever since that day when it was just like from that day it was really bad. It was all spread out, and you could basically tell that one half of the data showed that there was all of this flux on the left-hand side, which corresponds to the blue shifted. Yeah, so this side, as you march along the wavelengths, this is basically the blue side and the red side. And all of the blue data was pretty much skewed way too much from this condensation, I think.
I'm so tempted to fly to New Mexico and push the spectrograph off in the mountain.
I mean, I remember you saw it is on a cart, so you could.
Yeah, so there was no way to tell where it started and where it ended, so I literally had to go through every single step. Oh, yeah, now we know.
September of 2017.
Yeah.
It's just been downhill since.
Yes.
Maybe it's questions for Mike. How could they ever allow condensation on the mirror?
No, it's not on the mirror, it's in the instrument.
Well, so there was a dewar leak, and for those people who don't know what a dewar is, it basically contains, cold nitrogen gas, which, helps out with the electronics. The CCD depresses the noise in the charge coupled device. And so at some point, there was a leak from the dewar into the spectrograph, and it started coating one of the optics lenses. So you get blurry images from that. And they periodically go in and clean it out, but it continues to happen. So good thing is that they built a new spectrograph, which hopefully Garrett and me and Bina are going to go out and use in Mexico in about a month or so. We'll see.
I could have said that, but I let Mike take the question, so. Thank you. Thank you.
And like I said, this was a multi-institutional summer. So our next speaker is Ramona, who is here from Agnes Scott.
Okay, so I'm Ramona Bailey. I'm from Agnes Scott, and I study the photometry of Delta Scuti variable stars. So first, I'd just like to acknowledge the SIR Observatory for letting me use it, and then these people for funding me. So first, I'm going to talk about the background on Delta Scuti stars and some other important stuff, and then my methods and results and conclusion. So Delta Scuti variable stars are pulsating variable stars that change in brightness over a period of time. Their spectral type is somewhere between F8 and A2, and they're somewhere from 1 to 2.5 solar masses. All of them have a pretty low amplitude, which just means that they don't change in brightness very much, and they all have short periods. I think all of the ones that I studied were somewhere between like 1 to 3 hours. This is an animation of how these stars kind of pulsate, and then the light curve of what it looks like when it's changing. So these stars lie on the instability strip, which just means that they undergo self-excited oscillations. So as the star compresses, the opacity increases, and it traps energy, and the star gets hotter and brighter. But then as it expands, the opacity decreases, and the star gets cooler and darker. So I studied these using photometry, which is a measurement of light. There are two different types of photometry that I used. Calibrated photometry, which measures the value of the variable star and the known magnitude of the reference star. So I'm able to find what the magnitude should be. And then relative photometry, which is the measurement of the brightness of the reference star and the variable star relative to each other. So with this, I can't find the value of the magnitude. I can just only see how much it changes. This is an example of a light curve of a delta Scuti star. So this is, what they all should be looking like. This is the telescope that I used. It is Roque de los Muchachos in Spain. It is a 1-meter telescope and an Andor CCD camera. I observed for 3 nights, 2 in June and 1 in July. So I had to calibrate my images to get some good things that were just data. So because all of this stuff is noise and dust on the lens and everything, and so I had to get something that was just stars and just data and looked nice like this. So first, how I would do that would be I'd take flats, which have donut-shaped spots from dust on the lens, and they're bright in the center from sensitivity differences. They account for imperfections on the lens and for atmospheric conditions. And so basically this is just subtracted from the light image, so none of it's there in the end. And they have to be taken at sunset or sunrise. This is a bias, which is just another calibration. It looks like static. It accounts for readout noise in the camera, and they're taken with the shutter of the telescope closed, and they happen instantaneously. And then the last one is darks, which just looks like static. It accounts for thermal noise in the camera. It's also subtracted from the light image, and it's also taken with the shutter closed. But they have the same exposure time as lights. So here are the stars that I looked at. I used calibrated photometry for most of them, which is what I wanted because I wanted people to find the magnitude. But I had to use relative photometry for a couple of them because there just weren't any stars in the field of view that I knew the magnitude of. So the way that I studied these was by taking images of a star for its full period. So I would start just at any time and then wait for it to get to its brightest point and then to its darkest point and then back up to where it was before. And then I'd created a light curve from the calibrated images, which is what this is here. And the variable star is the one right in the middle. And I'd compare its magnitude to the magnitude of a standard reference star somewhere in here that has a similar magnitude, but it doesn't change at all in brightness. All of my images were taken in the V filter. That's because magnitudes can be different in different filters, and I wanted it to be consistent. So this is my first light curve. It's probably my nicest light curve. I expected the magnitude to be around 13.1 to 13.7, and that's basically almost exactly what it is. It goes a little bit past 13.7, but it's still really nice. And I expected the period to be 0.06 days, and it is basically 0.06 days. You can see up in the top, the date is in Julian dates, which is basically just a number for a day. It's just the last few digits. This is another one of my light curves. It didn't turn out nearly as nice, and I think this is probably because its amplitude is so much smaller than the one of my last star. I expected its magnitude to be around 11.4, but it's actually a lot closer to the whole 11.6 range. And I expected its period to be about 0.05 days, and it is kind of 0.05 days, but at the end of it, it starts going down a lot steeper than where it did at the beginning. So I'm not actually sure if that's something that it's doing because it's funky looking, or if it actually continues to go on after it, and the expected period is not what I thought it would be. Here's another light curve that I have, which is really funky looking. I expected the magnitude to be around 12.8, and it's, I don't know, it's close to that, but it's closer to like 12.68, 12.7. But some of the points are like really high up at around like 12.5, and I'm not entirely sure why, but again, I think it's because the amplitude of this star was so small, so it's not quite as accurate, I guess. I expected the period to be 0.04 days, and it's close to that, but it's, again, really hard to tell because I don't really know what's going on at the end of it, especially because it's doing something weird. Here are two stars I had to use relative photometry with. I expected their amplitude to be, this one to be 0.15, and it's a lot like greater than that. I'm not entirely sure why that is. And this amplitude is also a little bit off. It's a lot closer than the other one, though. And their period is basically what I expected them to be. So what I can conclude from this really is that all of my light curves, at least all the ones that are, you can clearly see, they all have pretty similar shapes, which is that they go down slowly and back up quickly. And you can see that in my, like the example of the light curve at the very beginning. That wasn't mine, it was somebody else's. It also does that same kind of thing where it goes down slowly and back up quickly. So I could look at more Delta Scuti stars and see if they all follow the same pattern, because I'm not actually sure if they do. And I could also look at stars with larger amplitudes to improve the quality of my light curves. That's
Any questions for Ramona?
yeah.
Did you say if your record stars were in the same field of view or were they separate fields of view?
No, it's the same one.
Okay. That takes me my second follow-up question.
Okay. Yeah.
But I'm sorry if I missed this, but how are you getting your expected values? How are you getting that?
There's a website, the AAVSO. They were on that.
Okay, so these are previous observations
Yes.
that people claim that you're trying to test.
Yeah, I'm just seeing if it's. Yeah.
So the first view, it looked like the period was only a few hours long. It was like 0.0 something days.
Mm-hmm.
Right? But you don't have the whole thing in there. So as you're observing really limited, like you only have a certain amount of observing time, maybe not the whole night.
No, well, I mean, they were up the whole night. I observed all of them for the full period, for what I thought the full period would be. Okay. Yes.
Would it be possible to use a star in your field of view as a reference, even if you didn't know it's theoretical, to help calibrate it? Because it seems that maybe you have some issue with some variability that may not be purely due to the star.
Yeah. Probably, I guess. I don't know.
Yes. A random star, you're not sure if that star itself is very well.
That is true too.
Mhm.
Let's think a moment. All right, and next we're staying on our topic of stars, and our next presenter is Ellie.
Thank you. Hey everyone, my name is Ellie Lincoln. I've been working with Dr. Fabian Barone. Mostly what I've been doing is single stars, some type of image reconstruction. So I got a little bit of a level up this summer and working on my first binary. So I am looking at Spica, which is the brightest star in Virgo, Alpha Virginis. They are both B-type stars, so they're really massive stars, main sequence stars. They're beta Cepheid variables, so you see a little bit of a fluctuation in the light when you're observing, and they are really easy to observe because they're short period stars, so it takes about a little over 4 days for the two binaries to orbit each other. And the data I'm using is from Chara, and it was taken in 2007, 2012, and 2015, and it looks like there was an attempt to get the full period each time it was observed, but only was able to get about 11 of the 12 epochs. And so what I'm looking for is to reconstruct the surface features. So I'm looking for the limb darkening, which you can see down here. It's the intensity of light that you see from going from the center to the outside of the star. So a lot of limb darkening would be brighter in the middle and darker on the edges, and no limb darkening would be just a uniform disk star. And looking for star spots also, I'm not super confident that I'll find them because it is a B-type star, so I don't know, looking for really small spots, yeah, not super hopeful for that, but gonna keep an eye out. And this would be what it would look like to recreate from just a practice image that I've done in the previous summer, reconstructing a star spot. And also looking for the proximity effect, which has been found to be there in the data in Spica, but it's yet to be imaged. So this is a light curve done by Jason Oftenberg in 2015, and it was just a poster, so I don't have a lot of details about it, but he claims that you can see evidence of the proximity effect in this light curve. And this is some reconstruction using the light curve data of Spica. So Fabian sent me some data from Chara, and he sent me this image that was done using the light curve inversion. Said, take the Chara data and try and make it look like this. And I don't know if anybody has seen Nailed It, but if this is what I was trying to make, this is what I made. So had a really hard time trying to figure out how to center the primary star, because that is a big deal with the visibility function that I'm using. It's assuming that the primary star is centered at 0. And I thought I had a really clever way to put it at 0 and shift everything around, but it turns out the function I thought did that does not do that. So that is to be decided. Meanwhile, I'm trying to fit my data. It looks much nicer when it's orbiting the center of mass. So this is my model of the visibility squared, square visibilities versus the actual observed data. It's not a very good model, as you can see. I don't know if that's because of the parameters I'm using. All the parameters I have are taken from Oftenberg and his previous observations, and he's working on a big manuscript right now, so I don't really have a lot of references on how the parameters were found. And the other thing could be I just have a bad visibility function. So my advisor Fabian and I chose this visibility function together, and we thought it was pretty accurate, but I don't think it is. So because it's a binary star, we can add the complex visibilities together, but there needs to be a translation applied to the secondary star. But I think also to the primary star, because as you could see in the previous few slides, it's not centered at 0 yet. So they both have a shift from the center of the plot. And so this is just the translation, the shift right here. You see with alpha naught and beta naught being the original location of the star, and alpha and beta being the shifted position to 0. And so to find what could be the best position, if I have the primary star centered at 0, I ran a grid search for the secondary position. So to show you, again, based on this original image, what that would look like. This is where the geometry places it, which I think Arturo is here. Arturo, thank you. Yes, he did all the hard part writing the geometry code, so I didn't have to do that myself. And so it looks pretty close to where they placed it using the light curve code. And then when I get my grid search, it's all the way out here. So not really confident, don't like that. It gives me an okay chi-square value, but it just doesn't. I don't trust it at all. And then even my model hates it. So if this is the first one I showed you with the geometry position, and then with the grid search position, it doesn't get much better. So still got a lot to do in fitting that. And my chi-square map doesn't even look good. So I kind of think it is a visibility function, because my chi-square map should look kind of like a topographical map, and it could kind of converge to a minimum. This is just kind of like, I don't know, your star could be anywhere on this map. So not super hopeful about that. And this is where the best X position for all the epochs would be. And I can maybe convince myself that there's kind of half an elliptic shape there if this is 0, 0. But then you still have like this guy, where's the laser pointer on this? Like way out here. So I don't trust any of the grid search, especially not for the flux. So this is supposed to be a chi-square map for the flux value, which turns out the flux isn't even considered as a variable in my visibility function. And my advisor right now is in France, so it's been kind of difficult to communicate, and I have tried to be like, I think I need a different visibility function, and it was kind of like, no, the one we have is fine, and I'm like, okay. So I changed the temperature. So it's a uniform temperature applied for both stars, and so I had the primary star fixed at one temperature, and so I let the second star loop through various temperatures, and my grid search just kind of gave up on me. So for now, this is me until my advisor gets back, just kind of looking for answers in all the wrong places. So what I want to do first is improve my model fit, because there's really no point in going on to the actual reconstruction if my model fit is garbage. So the orange is is what I would like my model to look like, but it aspires to be. And then this is kind of what I already have. So I either have bad parameters or a bad visibility function, and either way, there's no point in going on to the reconstruction if the model looks like this. So I either need to center the primary, try that, add a translation to both stars, tried different visibility function, and also while preparing for this talk, I reread my favorite paper, Berger 2007, for the 50th time, and realized that it should be in polar coordinates, and I'm not confident that it's actually, the shift is taken in polar coordinates yet. So something else to look at. And that's all I have for now. I didn't make an acknowledgement slide, but thank you to Fabian, thank you to Arturo for writing all the hard code, and thank you for Rachel and Brendan for the summer seminar. So thank you.
Okay, any questions for Ellie?
First of all, welcome to grad school.
Thank you.
There's a bunch of data, you figure it out while I go to France and you can
That's about right. Yeah.
Again, along the same thing, given that your advisor is currently out of country, would it be safe to say that all the difficulties you're currently having is his fault?
We can say that. I'm okay with that.
Your work is exemplary. It's all
I like that. Yeah.
I want to give you credit. That is the boldest approach to a talk that I've ever seen. Everything I've done is broken. Thank you.
Well, I had to show some kind of progress.
I am impressed.
Thank you.
And as we talked about in seminar, that is science a lot of the time, so.
Right. Rachel wouldn't let us call them problems. They're challenges.
So I was most disappointed that the nail it gun didn't come out of it.
I couldn't download that GIF. I tried. Yeah. Yeah, okay, fair. I didn't touch on that much, but go back. Right, so this is, I'm not sure how much different it is from what qualifies it as a beta Cepheid variable, but it's supposed to be some reflection of one star on the other when they're close to each other in the orbit. Yes, thank you for asking that. What's that? That I'm also not sure. Because I lifted it from a poster, so the poster didn't really touch on it because it wasn't looking for this, but it said here's some noise. It's probably due to a proximity effect. And they mentioned at the end that they are going to try and model it in a future project, but they didn't have, their computing wasn't strong enough to actually model that yet. So I would also like to know.
Let's thank Ellie again. To round out our symposium today, we will conclude with our second group effort, and that is Team Muon.
Are we allowed to use that mic too, since there's two of us?
So that is for YouTube recording. That's
so we need to share this.
You have to share. Yeah.
Okay. Here, put this in your pocket since I don't have any. Do you want the clicker or do you want the Okay. Okay. I'd like to start by thanking you all for staying this late.
The very end of a talk is the hard part to get to. So, hello, I'm James Schur.
I'm Natty Katab.
And working under Dr. Xiaoshun He, we are studying low-cost cosmic ray neutron and muon detection. Before we get into what muon and neutron detection entails, we must first discuss what cosmic rays actually are. They're split into two types, primary and secondary cosmic rays. Primary cosmic rays are high-energy nuclei that hit the upper atmosphere, and they interact and cause what's called an air shower of secondary cosmic rays. These cascade down and eventually decay into muons and neutrons, about 80 and 20% respectively, at the surface of the Earth. You can see in this picture an example of an iron nuclei primary particle decay chaining into the middle button, into muons.
So the first cosmic ray measurements were actually made in 1909 by a man named Theodore Wolff. He wanted to take cosmic ray measurements from the highest altitude possible, and in 1909 the tallest building in the world was the Eiffel Tower. So he took a homemade electrometer, climbed up to the top of the Eiffel Tower, and took what we know to be the first recorded measurements of cosmic rays. However, the paper he published didn't get very popular, and no one really paid any attention to it until in 1912, a man named Victor Hess decided to revisit the study but do something much more in-depth. He used much better equipment, and he took cosmic ray readings at multiple altitudes, including top of the Eiffel Tower again, ground level, and even below sea level. The results that he found showed that higher altitude was directly correlated with more cosmic particles. So he theorized, okay, this must mean that cosmic particles are coming directly from the sun. So he did a follow-up experiment where he took the exact same readings at the exact same altitudes during a total solar eclipse. And if his theory was right, that cosmic particles were coming from the sun, that would show different readings during a solar eclipse. But that was actually the opposite of what he found. When he took the readings during a solar eclipse, it was the exact same as in full sunlight, which indicated that the cosmic particles were actually coming from the atmosphere and not the sun itself. And later, in 1936, he won the Nobel Prize in Physics for this research. So what are we using cosmic rays for today? Because cosmic particles, specifically muons, are generated by the Earth's atmosphere, by taking precise enough measurements of the behavior of muons, we can take live readings of weather conditions in the upper atmosphere. Currently, the way that modern meteorologists take weather readings is twice a day, once every 12 hours, they send up a weather balloon. And it takes as many measurements as it can from temperature to humidity, sends the readings down, and the meteorologists use that to make more or less an educated guess for what the weather's going to be like for the rest of the day. Which is why when we check the weather in the morning, we're given a % likelihood of certain weather conditions instead of a yes or no answer, do we need an umbrella? But with cosmic ray measurements, we can get live minute-by-minute updates of the weather conditions in the upper atmosphere, which would take the guesswork out of meteorology and allow us to make more accurate weather predictions than ever before.
2 slides ago, you saw a more historical effort to measure cosmic ray counts, but there are also a number of modern efforts, particularly in monitoring neutrons, as it's much more difficult than monitoring muons because neutrons are uncharged and interact less with particles because of that. On the right here, on the left here, you can see worldwide locations of neutron detectors that have been running, some of them since the late 1960s, going back as far as that. And on the right here, you can see a boron trifluoride neutron detector. It's very large, and while it's efficient, it's not portable and expensive, and that brings us to our main design goals, which we're trying to keep the cost as low as possible while also being able to deploy them worldwide and having them be very portable.
So what you're seeing on the table is our actual muon telescope. That is the whole thing. We designed these to be as light, as portable, and as durable as physically possible. So it consists primarily of 3 scintillator tiles stacked on top of one another, a neutron cell which can be added or removed depending on if we want the neutron cell to be a part of our readings, and a Raspberry Pi on the bottom, which is pre-programmed to collect all of the data that we need from the tiles. So these tiles are pretty simple. It's just a scintillator tile wrapped in light-proof material, and when a muon hits the scintillator tile, it releases a couple hundred photons, and we get a reading saying, okay, a muon hit, it released some photons, here's how the muon is behaving. We have 3 tiles stacked on top of each other because the more tiles you have, the less likely you are to accidentally get false positives in your data. For instance, if a muon hits the telescope diagonally, then it'll only hit one of the detectors and not all 3 of them, which is good because we don't want diagonal muons. We want to detect muons directly above the telescope. So by stacking the tiles on top of each other, we're able to make sure that we're only getting muons coming from directly above us in the atmosphere. Yeah.
And the other portion of the detector that she mentioned is this neutron cell here. As I mentioned earlier, it's much more difficult to measure neutron counts because they're uncharged, and therefore it's much less likely for them to ionize particles. One of the other most common ways to measure neutrons is a liquid scintillator, as opposed to the hard plastic scintillator you can see there on those tiles. They are sensitive to both muons and neutrons, and you can see on these end caps here, there is a small hole where a wavelength shifting fiber comes out, and this can be read by one of the silicon photomultipliers. A glass tube goes down filled with optical grease into the tank to detect the light and collect it out. In this, all the data sent from these tiles and from this neutron cell is sent to custom designed telescope readout boards. Here in the bottom right, you can see one of the silicon photomultiplier boards, and this is where the silicon photomultiplier goes. These attach to either the side of the plastic tiles or they attach to the end caps on the neutron cells. And this is read out through an Ethernet cable to one of these custom 4-channel boards. This interfaces onto a Raspberry Pi, which is what's used to collect the data and output it and save it. On here you can also see 4 voltage boards because the silicon photomultipliers work at about 55 volts, and the power that the Raspberry Pi is getting is about 5 volts.
So there are a lot of steps that go into designing a muon telescope before we actually hit the building phase. As you can probably guess, we don't want to waste the time, money, and resources building a model of a telescope and then deciding, nope, we don't like that one, we're going to do it differently. So 3D modeling is actually a very big part of that. I was actually brought onto the team specifically because I have 5 years worth of experience using Autodesk Inventor. So as soon as I was hired, I hit the lab with a caliper and a muon telescope and rendered every single piece that is a part of this telescope in Autodesk Inventor. And the 3 pictures you're seeing here are essentially the final products. The one you see on the far left is just the muon telescope without the neutron cell. The one in the middle is the muon telescope with the neutron cell incorporated, and this one right here is a disassembled model of the neutron cell, so you can actually see the 2 glass detectors inside the neutron cell, and then this would be filled with liquid scintillator.
I actually mentioned these 3D models are going to be used to help simulate the detector. We use what's called GEONT4, which is a particle physics simulation package to monitor the detector's acceptance for particles. You can see here just an example of the angle of acceptance that we're getting from particles, and you can see on the right here an example of 102 gigaelectron volt muon events. The red is the negatively charged particles, green are neutrally charged particles.
So there were actually a lot of steps that went into getting to run the GEONT4 simulations. There isn't exactly a how-to guide out there for converting Autodesk Inventor files into GEONT4 files, so we were essentially wandering through the forest blind on this one. So we spent a whole week stuck in file conversion limbo trying to turn that Autodesk Inventor IPT file into this GEONT4.gdml file. And we found the most efficient way to do that was to convert IPT to STL and then STL to .gdml, which sounds ridiculous, but that's how we got to do it. So the one you see on the far left is the .ipt file, which is a traditional Inventor file. The one you see in the middle is an STL file, which is essentially a simplified 3D model that doesn't care about how many pieces are involved. It just shrinks the whole thing down into one giant piece. And then the .gdml file here was the final product, which is even more simplified, and it only incorporates the vertices of the final product to get a 3D model